Swayam Prabha. Digital India. Educated India.
So, this is basically what we saw in the last class. We got the in the solid phase, we have the unsteady state heat conduction equation, and I am using this definition for the similarity transformation. Okay. This is slightly different from what we did in the Rayleigh problem. When we did that earlier problem where we had the plate moving, okay, I did not have this factor of 2. So, now I am having this factor of 2. I mean, so basically the point is things still work irrespective of what this factor is. So, if you remember when I said there is an alternative method for calculating this finding out this transformation, I assumed some g of t and we got an arbitrary constant. So, this arbitrary constant does not really change anything. The only thing is in the earlier case I think we had only eta, now we have 2 eta, okay. And what this means is theta s. So, this means, so this is correct, and I can write this equation as d by d eta, or I say let d theta s by d eta be equal to some g, then this becomes dg by d eta plus 2 eta g equals 0. Okay. So, all I have done is put the first derivative equal to g and I have got this. Now, when I solve this, I get, when I integrate the equation for g, I get g of eta as, take it to the other side, do your cross multiplication, g comes to the bottom, let me do this, dg by g equals 2 eta d eta with a minus sign, okay. And so, g of log of g eta is minus eta squared plus log k or log C1, some arbitrary constant. So, g of eta can be written as C1 e power minus eta squared. So, the advantage of choosing the factor of 2 here is that I directly got e power minus eta squared, because that is what is coming in my error function. Earlier when I did the Rayleigh problem, I had e power minus eta squared by 4, and then I had to do a substitution of variable, I defined s by 2 equal to r, and then I proceeded, okay. So, now by putting in this factor of 2, what I am getting is g is this. So, that means d theta s by d eta is C1 e power minus eta squared, okay. And now I can integrate with respect to eta on both sides, and maybe, so integrating on integrating this equation, I get d theta s, because I want my solution in terms of eta, okay. And if I integrate with respect to eta, then this eta, and again I put in the limits, I have a problem. And when I am integrating, remember integral f of x dx, f of y dy are the same. So, I can put a dummy variable, okay. So, I am going to write this as d theta s C1 integral e power minus u squared du, okay. And when this is a dummy variable, okay. When it is 0, when z is 0, what is theta s? Theta s is 0, okay. I am integrating between limits, and then I am integrating it to an arbitrary point eta s, where it is theta s. So, what I am doing is I am integrating this equation between limits. Okay. This is at an arbitrary location eta s, arbitrary location eta s, my temperature is theta s. At the boundary where z is 0, eta s is 0, okay, and you remember represents eta. So, temperature is 0. This is one way to do it, and what this means is theta s is nothing but C1 times error function of eta s. Okay, because that is the definition of the error function. I mean, this is one way to do it. If you do not want to do integrating between limits, then you can just integrate this. Actually, I should put eta s, no, because yeah, I have two different etas in the two variables. So, put this as eta s, man, because I am doing it in the solid phase. Why is it eta s? Because in the liquid my thermal diffusivity will be different, alpha L. So, this is all eta s. So, this is the thing. You can, if you do not want to do definite integral from between limits, you can just integrate without limits, then you will get theta s is equal to C1 integral e power minus u square du, okay, plus C2, an arbitrary constant will come, okay. And now, how do you find that arbitrary constant? You put, oh, this is going to go from 0 to, let us say, eta s, because I want theta s to be a function of eta s. Okay. So, this upper limit is theta s, and now I can substitute at eta s equal to 0, C, this integral becomes 0, I will get C2 equal to 0, I get back what I got earlier, okay. At eta s equal to 0, theta s is 0, so I get C2 equal to 0, and I will get back the same thing. Anyway, whichever way you want, you can do it. So, now we need to figure out what is this constant C1, okay. For that I need to put the other boundary condition, which is at the interface, at the freezing front, what is the temperature? Temperature is going to be the melting point theta m, okay. At Z equals Zm of T, eta is eta Sm, okay, and that is Zm of T divided by 2 times square root of alpha St. So, what have I done here? I am trying to find this other constant, okay, C1. I found C2 using boundary condition z equal to 0. I am trying to find the boundary condition C1 by finding the this thing. So, and here theta is equal to theta m, the melting point. So, I put theta m equals C1 times error function of what? I have to evaluate this at the melting point, right. So, this is at the front. So, at eta Sm is when z is equal to Zm, okay, this is eta Sm, this is my this thing. So, now the question is what can I infer from this? I can say that this guy is a constant. Why? Because it is a melting point, it does not change, melting point of a substance is fixed. This is also a constant. So, if this is a constant, that is a constant, it means eta s comma m has to be constant, okay. this implies eta s comma m or eta sm equal to a constant, and this means Zm by t divided by 2 times square root of alpha s t equals a constant which I am going to say is beta. Okay. So, the constant. I do not know what beta is. One of the things I want to do is find out beta, because only if I find out beta I can tell how Zm of t is changing with time. Actually, if I want to quantitatively understand, but what I can find out from this, what I can infer from this is Zm of t is equal to beta times 2 times square root of alpha s t. It has a square root dependency on time. Okay, it is parabolic. So, I know how qualitatively Zm is going to change with time without doing any calculation. I can just get that insight. Okay. So, this is basically what I get. So, beta is a constant to be determined. Okay. But we have found that Zm has a t to the power half dependency. Okay. So, basically we plot Zm versus t, initially interface is at 0, okay, and then goes and saturates. So, it means a parabolic. So, it is fast initially because there is less resistance to the heat transfer. So, it goes the freezing, a lot of ice is formed very quickly, but as the interface goes higher and higher, the resistance to the heat transfer increases. So, the process slows down. So, Zm starts moving slower and slower. That is basically what you are seeing. Okay. So, without making much of a calculation, we are able to come up with this inference. Okay. This is only a qualitative shape. If you want to get the exact quantitative shape, I need to find beta. Okay. So, for that I will do some more work, which is finding out what the solution is in the liquid phase. I have solved what is it in the solid phase. Now, I have to find out what it is in the liquid phase. So, find beta, we need to solve for liquid phase, the upper phase. Okay. Again, the equation which we wrote was d theta L by dt equals alpha L d squared theta L by d z squared. Okay. See, remember we just said only conduction is happening, no volume change because of the freezing. So, only conduction. Only thing is the properties of the liquid are different from the properties of the solid. So, it is alpha S, I have alpha L and theta L. So, now I am going to define my similarity transformation variable eta L as Z divided by 2 times square root of alpha L t. Again the factor of 2 is just to make it easy, and what will you get if you were to, if you do this again in terms of eta, what do we get? D squared theta L by d eta L squared plus 2 eta L d theta L by d eta L equal to 0. That is what you will get. I mean, if it, because the equation is the same for theta S and theta L, only alpha S and alpha L are different. You go through the same procedure, and if you get it right, that's what you should get. So, the solution is going to be again similar, again in terms of error function. Only thing is, now I have to understand theta L is going to go from Zm to infinity or eta Lm to infinity. Okay. This solution, this is valid in the liquid phase, where Z is greater than Zm or eta L is greater than eta Lm, which is Zm by 2 times square root of alpha Lt. Okay? Because liquid is only above the point and Z equal to Zm is my interface. Is this clear? So, again do the same stuff. You will get d theta L by d eta L equals e power minus eta L squared with a C3, I think, C1, C2, C3, yeah. Okay. You will get, exactly what I did earlier. The derivative we got as e power minus eta squared, remember? Okay. Because this 2 is there, get e power minus eta squared directly. And then again I integrate it one more time, I get integrate again I get I will use it the other way, theta L of eta L is integral C3 from eta L to infinity e power minus u squared du plus C4. Okay. Basically, I am just trying to tell you, I have not put the limits on the theta L yet. So, that is the reason, and this arbitrary constant is coming in here. Okay. And in the liquid domain, the extent is from eta L m to infinity, so eta L to infinity. Okay. Now, how do I find C4 and C3? Same method. So, this is basically whatever we did earlier for the solid phase, I am doing it here. Integrate, you get this. Integrate one more time, you get that. So, at eta tending to infinity, what is theta L? Theta L was T1, and if you remember, theta L was 1, because this is 0, that was 1, right? Theta L is 1. So, if I put eta L equal to infinity, here this is upper and lower limits become the same. So, this goes to 0. So, C4 is 1. Okay. And how do I find C3? I put the other boundary condition. Other boundary condition is at Z equal to Zm or eta L equals eta Lm, which is Zm of t divided by 2 times square root of alpha Lt at eta Lm, theta is L equal to theta m, the melting point. Okay. So, now I use this boundary condition, I get theta m, eta will be at the interface, eta Lm. Infinity plus 1. Okay. So, you can find C3, and C3 will be theta m minus 1 divided by integral eta Lm to infinity e power minus u square du. So, basically I found all my constants and I know my temperature profile. Okay. So, it looks like I have solved the problem, right. I found the theta L and theta S, how the temperature varies, because I know the constants, you can substitute it. Error function is something you can go to one of the software packages and make it plotted, you will get it. Okay. So, basically theta L is this. So, theta L will be you substitute for C3 here and C4 here, you get it. I am not going to keep rewriting the equation. Okay. So, we have found theta S and theta L, but have you completely solved the problem? The answer is no, because I am more interested in the front, where exactly it is. Okay. I want to find out Zm, how is that changing with time? Qualitatively I told you it is square root, I do not know what beta is yet. Okay. I am yet to find out that constant beta that I spoke about earlier. How do I find that out? There is one more condition which I have not used, which is that condition, this is the heat flux condition. Okay. So, basically what you have to do is you have found the theta S and the theta L, you go to the heat flux condition, you substitute this theta S and theta L there and find the beta, find the how Z is changing with time. Okay. That is the idea. To find Zm of T, we use the heat flux condition. Okay. And remember the heat flux condition was KL, oh boy, okay, S by dz plus what was it, rho times L times dzm by dt. Okay. So, what I am trying to tell you is I found it in terms of dimensional variable theta L. You can substitute everything back. I am not going to do it, I am going to leave it to you to do it. So, you have to write everything, you found out theta L, theta S. So, substitute it back in terms of Ts, whatever it is, or you convert this to dimensionless form, it does not matter, and then calculate the theta L derivative, theta S derivative, substitute it here, and then convert it to eta again and proceed. Okay. So, using this we find beta. Okay. So, I mean more than finding the actual solution, because how the derivative of the error function works, I mean it is just e power minus, because the error function is integral from 0 to eta, the derivative will be just the integrand e power minus eta squared. So, it is not a problem. So, you can find it and you can substitute it back and calculate what the beta value is. That will tell you the quantitative thing. Okay. I think what you people should focus on more is not, I mean of course you get the right solution, right, but focus more on the approach and understanding what the approach is, and if you understand the approach, then finding the derivative and substituting it and then calculating the beta value and all that is straightforward. So, the whole point of me taking so much time to explain all these things is just to tell you that you should focus more on the approach and understand what the physical problem is. Okay. So, now of course, we have made a lot of assumptions, and if you are doing an experiment and if you find out that Zm as a function of time is coming completely different from what you are predicting using your calculation, then you have to go back and see if you can relax some of the assumptions, maybe the density change, maybe you are assuming temperature is not varying radially, all those things. Okay. So, you can change those assumptions and then rework the problem, but you may not be able to get neat results, analytical results like this, you may have to do it numerically. So, when you do it numerically, you can, under some limits you can match your numerical results. When you do it numerically also, you need to be confident that your numerical results are correct. So, under some assumptions the numerical results will collapse to the analytical solution we have got, okay, maybe very thin diameter of the pipe, for example, or very high thermal conductivity, I can say the cross sectional temperature is uniform. So, those kinds of things we can do and verify. So, at the end of the day you have to verify, you can verify this prediction by experiments, you can do numerical calculations and verify what we have done, okay. So, to just make sure that whatever we have done is right. So, that is the idea. So, as long as you understood the approach, so focus more on formulating the problem, understanding what is the question you are trying to answer, formulating the problem, then coming up with the method to solve and then solving it, and then that is it, okay. Okay. Now, I want to go to a slightly any questions? Familiar problem which most of you are familiar with, okay, and that is let us say transient heat conduction, transient heat transfer from a solid sphere in an unbounded fluid. So, basically you have some hot sphere, spherical body, okay, you are dipping it in a liquid which is at let us say ambient temperature. So, this guy is going to cool down, okay, the hot sphere is going to cool down, and what you are interested in is finding out how the temperature is going to change with both the position and time. So, what do I expect? I have this sphere and let us say this is at Th hot and Ta is the ambient, okay, A for ambient, H for hot. So, I have this hot ball in ambient liquid and this is going to clearly this is going to cool down, okay, and the ambient liquid is so large that the temperature of the ambient liquid does not change. I am assuming Ta is constant, okay. This is constant if the fluid has large volume. That is the reason I said unbounded liquid, okay. And if you were to plot as a function of r the temperature, okay, and this is let us say the radius of the sphere is capital R. I am interested in outside the sphere there is no change, temperature is Ta. I am interested in what is going to happen inside the sphere, okay. At time t equal to 0, temperature is going to be uniform everywhere at Th. This is R. Everywhere it is because this fluid, I mean, more uniform temperature Th, okay. So, this is Th. As time progresses, if I want to ask you to sketch how does the temperature change inside my sphere, the portion near the ambient is the one which is going to cool down first, correct, because this is the center of the sphere, this is in the center. So, that is going to cool down last. So, what is going to cool is first the periphery. So, I am going to get Th here and then somewhere here is going to cool down, okay. So, temperature is going to decrease in the sphere, but the decrease is going to be first near the periphery, near the surface, and this temperature is T ambient, let us say. And as time progresses, as time progresses, what is going to happen? This guy at center of the sphere will also start decreasing by conduction. Okay, this is also going to lose heat, and slowly I will get something like this, and eventually I will get T ambient. So, you understand that initially my sphere is at TH. Finally, if you wait for a very long time, this sphere is going to lose heat, ambient is at T ambient, and everywhere, because this is heat transfer by conduction, okay, everywhere if there is a temperature gradient, temperature is high at some point, it will lose heat, it will get conducted away and it will decrease, eventually it will become TA everywhere, and my initial profile is like this. This is at T equal to 0, and this flat profile is at T equal to infinity, it is uniform. Okay. So, at T equal to 0 is like a step function, and at T equal to infinity it is uniform at TA, and this is how it will be. First cool periphery, slowly starts cooling inwards, this guy will cool first, then this guy will cool last. I have only drawn this qualitative sketch. What we want to do is we want to quantitatively understand how does this change. Okay. So, temperature clearly is a function only of R and T. I am assuming that it is one dimensional, no variation in the theta and the phi direction, and we are working in spherical geometry. Okay. So, again our objective is to find T of R comma T. I mean, you have done this problem, I am sure, before, and the equation is dTs by dt equals Ks by R squared d by dr of R squared dTs by dt dr. So, I am basically balancing this energy equation. Yes, I am looking at inside the solid, there is absolutely no convection, only conduction and only in the radial direction, okay, and then the accumulation term, which is this term. Okay. So, I need to solve this problem, and the boundary conditions are at R equal to 0, my Ts is bounded. I need to get a bounded solution, and at R equals R, what is going to be my boundary condition? There is going to be heat flux. See, if this guy is adiabatic, if it is insulated, there is going to be no change in the temperature, this is losing heat. Okay. And the simplest boundary condition to think of is the Newton's law of cooling, where you say minus Ks dTs by dr equals H times Ts minus T ambient. Okay. So, this is basically again just the flux balance at the interface. This is the conductive flux. Whatever heat is being conducted from the solid to the surface is basically going to leave from the surface to the liquid, but through the heat transfer coefficient, Newton's law of cooling. Okay. So, this is flux balance. This conductive flux and this is convective in the fluid, and this is in the solid. Of course, I need to get one more condition, which is the initial condition, because this is second order in R and first order in time, and the condition is at time t equal to 0, my temperature Ts is equal to Th. Okay. At t equal to 0, temperature Ts is equal to Th, that is my initial temperature. So, with these boundary conditions, you can actually solve the problem. You can solve this problem using separation of variables. Okay. And I am not going to talk about separation of variables here, this is very standard method, but what I wanted to do is, you have also done the problem of heat transfer from a sphere in the limit of low Biot number or high thermal conductivity. Okay. So, what you do is, when the thermal conductivity is very high, you use a lumped model and look at the heat transfer problem, right. So, I wanted to basically show how I can derive that equation starting from this equation. Okay. I mean, there is a very formal mathematical method of doing it, but that is a bit complicated. So, I am going to use a kind of a physical argument and then proceed to make it a bit more simple. So, how does this simplify if K tends to infinity, Ks, the solid thermal conductivity. Okay. So, what do I expect? When the solid conductivity is very high, I am expecting that the temperature is going to be uniform everywhere inside. Okay. Because if you have very good conductor, it will quickly conduct the heat and you can neglect radial variations. Okay. So, here if there is a temperature gradient in the r direction, it will quickly become uniform. Okay. So, yeah, I will do that later. I wanted to draw a picture, but I will draw that picture later. What I want to do is, I want to take this differential equation and I want to integrate it in the radial direction by considering a spherical annulus. So, integrate the PDE in the radial direction. That is, I am going to multiply this by 4 pi r squared rho s, let me put this alpha s man. So, I have dTs by dt times 4 pi r squared dr equals, or maybe not, maybe I will keep this as rho s CPS, yeah, is equal to Ks by r squared So, because it is a sphere, I am considering, I am doing this integration from the whole body of the sphere, okay, and I am taking, this is written on a per unit volume basis. Remember, this particular energy balance is written on a per unit volume basis. So, I am just considering a small volume element. This volume element is 4 pi r square dr for in the spherical geometry, okay. So, I am just multiplying by dV and now I am integrating this from 0 to capital R. Okay. The right hand side is integral. So, this is the right hand side. So, r squared dr cancels off, okay, 4 pi, I think I will let the 4 pi be there, okay. So, I get Ks times 4 pi, okay, d of r dTs by dr from 0 to capital R, okay. I am taking 0 to r, Ks comes out, 4 pi comes out, and this r squared and that r squared cancel off, and I have just d of that. Okay. So, now I have Ks 4 pi, this is multiplied by r square dTs by dr evaluated between 0 and capital R. Well, integral of d of that is just that. So, this is Ks times 4 pi times evaluate this as capital R, I get R squared times dTs by dr evaluated at R equal to R, and at 0 it is 0 because R squared is 0. Okay, that is what this is. From the boundary condition, what do I get? From the boundary condition, I know Ks dTs by dr is heat transfer coefficient H times T minus Ta or minus of that. Okay. So, from the boundary condition, this is equal to minus H times 4 pi R squared times T H minus Ta. Okay, because that was the boundary condition I had. Maybe I should put Ts, no? Why did I change this? Ts, sorry, Ts. So, yeah, this is the right hand side. So, the left hand side is rho s Cps integral 0 to R, what is it? D by dt of Ts of R comma T times 4 pi R squared dr. Okay. And because I am integrating in the radial direction, derivative with respect to the time, I can interchange the order of integration and differentiation. I can go 0 to R Ts of R comma T times 4 pi R squared dr. Now, I have in the limit of large this thing, the limit of large conductivity, I am telling you the temperature will not change in the radial direction. Okay. So, this becomes independent of R and I can pull it outside the integral. Okay, because for large k, we are looking at large k, this implies Ts is independent of R because uniform. Okay, if you have copper, the temperature will be uniform everywhere inside as opposed to something else which is less conducting. So, it is independent of R, integrating in the R direction, I can pull this out and I get rho s Cps dTs by dt integral 4 pi R squared is 4 by 3 pi R cube. Okay. So, basically what you end up getting is rho s Cps multiplied by volume times dTs by dt equals minus H times surface area 4 pi R squared times Ts minus Ta. Okay. So, this is possibly something which again you are comfortable with, familiar with in the context of transient heat conduction, you must have done in your BTech, okay, in your undergrad. So, where you got this is called the lumped heat transfer equation, lumped because all the spatial variations are now neglected, or so from partial differential equation I have got an ODE now, okay, and I can use this. So, basically I wanted to show the transition, how from the partial differential equation which where you have temperature as a function of R and T, I have now got an equation which depends only on T, and because now this depends only on T, I should use a total derivative, not a partial derivative, okay. So, you should keep that in mind because now it depends only on time. So, this is my lumped energy balance, and you saw, so and this is again the argument which we made when we were doing that freezing problem. When we did the freezing problem, I said I am neglecting temperature variation in the radial direction, okay, in the r direction. I can do that as long as my thermal conductivity is very high. So, physically I can justify assuming temperature does not depend upon the radial direction for large k values, okay, and that is basically what I am trying to show you here. So, the large k values I can neglect this thing, and kind of this is actually not a very formal mathematical derivation, okay, but just to give you an idea of how I can go from PD to ODE using some physical arguments and some mathematical. If I do the strictly mathematical, so now what happens here, this is the last thing, there is a small boundary layer kind of thing which is developed. So, now if I were to plot, temperature of the solid versus R, initially it is TH, then it is TA, I will get some uniform value, and there is a small region where it will quickly go to 0. So, you understand? So, basically, so again this is at t equal to 0, this is t equal to 10 seconds, this is t equal to 20 seconds, whatever, but there is uniform everywhere, it is cooling down, it is uniform everywhere except for small region where it has to be some value, it has to come to ambient temperature soon, okay. So, there is a sudden drop. So, basically what I am trying to tell you is there is a thermal boundary layer over which the temperature suddenly changes, okay. I mean that is the way. So, there is some kind of a singularity there. So, I mean it is not a perfect solution, but just to understand how it works, okay. So, if you had finite conductivity, it will be smooth profile because conductivity is finite, but here the lumping tells me, and it has to match this boundary condition. So, you have this discontinuity, okay. Thank you.